Hello class. So we'll continue with chapter 8, Differential and Multistage Amplifiers. We're still in week 7, and in the first part of week 7 we looked at sections 8.1, where we were introduced to the idea of a Morse differential pair, and we were introduced to this way of connecting two Morse transistors so that they form a pair, and then you can apply the input to both gates in a differential form or in a common mode form. So we studied that in the last recording, and similarly we also looked at the BJT equivalent of the Morse differential pair. So that was section 8.3. So in this recording, we address topic 8.2. Firstly, I'll do a lecture, which is this recording, and then I'll do on the same topic some examples and problems in the next recording. So 8.2 is all about small signal operation of the Morse differential pair. So far we've looked at the circuit drawing, we looked at some DC bias requirements, we looked at the large signal formulas for current and so on. Now we'll specifically focus on the small signal operation, more importantly gain, right? Because as an amplifier we are most interested in gain in the linear region, and so some formulas for how to find the gain. Also, one of the big reasons obviously why we use the differential connection is to reject common mode signals. So if you have a small signal that needs to be amplified, but that small signal is riding on some high value voltages, then you don't want that high value voltage to be amplified, right? You want it to be rejected. So in this section, we define a way of understanding how well our differential circuit is able to reject common mode signals but only amplify differential signals. So those are all the topics in under 8.2. So I'll also look at 8.3, which is the BJT equivalent of this, very quickly. I mean, I'm not going to spend too much time, but we'll also try to at least become familiar with the point that for everything we study with Morse devices, there is an equivalent with the BJT devices also. Okay. All right. So I am on slide 23 of my PPT on chapter 8, and this is the first slide of topic 8.2, small signal operation. So we see a small signal, well, a Morse differential amplifier. We have seen this kind of circuit before, and the inputs, there's two here. We know that the inputs can be applied in a single-ended fashion or a complementary fashion, right? Single-ended means all the input is applied into one gate or one input point, and the other input point, which is the other gate, can be straight grounded. But this drawing shows you VG1 and VG2 as 2 points to apply the input. The output, as you know, can be taken differentially, which means between these two terminals, or you can take it again single-endedly output. That means if you take it VD1 to ground or VD2 to ground, that would be called single-ended output. If you just take between VDN and VD2, that would be called differential output. Okay. So the drawing is titled Figure 8.8 Small Signal Analysis of the MOS Differential Amplifier, and I'm defining a couple of terms again. VCM, capital CM, is the input DC common mode voltage, and then VID is the differential input signal, right? So VID is a small one, small I, small d. VCM is a common mode input DC voltage. Now, what is the difference between VCM, VG1 and VID? You need to understand that. So the input at the gate consists not only of the signal but some DC voltage, some kind of biasing DC. This may or may not be zero, okay? And so here we study when it can be zero. So the circuit shows a common mode voltage VCM applied to set the DC bias voltage at the gates. So this VCM is part of the biasing business, so you can't avoid it. And the input signal VID is applied in a complementary or balanced manner. So what that means is the VID, whatever is the input signal, is divided into two parts. One part is applied, one half is applied here, the other half is applied here. Okay, in a complementary or balanced fashion. Now VG1 is defined as the voltage at this gate is the sum of VCM plus half VID. VG2 is defined as the sum of VCM minus half VID. Typically, VCM is the middle value of the power supply for the whole circuit. Now this is important. Where two complementary supplies, like in this drawing, you see there is a VDD and there is a VSS, right? So there's both a positive and a negative separately. Sometimes you'll just have a VDD and this portion is grounded, right? There's only, then you call it a single power supply. Here we call it a dual power supply. Let's say VDD and VSS are equal, and we say this is DD because of the drains here, SS is because of the sources, right? So in the case that VSS is equal to minus VDD, then the middle of this VSS and VDD just becomes zero, right? So typically VCM is at the middle of the power supply, middle value. Where two complementary supplies are utilized, VCM is zero. So this is a bit of an important concept. We'll do some problems where this will become clearer. But for now, make sure you understand why VCM is always shown, even though it may be zero. How we define the input signal, input differential, half of it coming here and half of it coming here. And how the VG1 and VG2 are slightly different from each other based on the values of VID. Okay. All right. With these three things, I will move on. Actually, I should also magnify this, I think. That'll help you. So we are on slide 24. Continuing, the differential input VID can be applied in a single-ended fashion, like I already said. If all this VID comes only here and this is grounded, then we call that single-ended. But the way we show it here is called complementary or balanced, as shown in this figure. Similarly, the output VOD can be taken between one of the drains and ground. So if you take it from here to ground or from here to ground, then we call it two single-ended outputs, VO1 and VO2, which is actually nothing but VD1 and VD2, to ground. If you take it between the two drains, then what you get is called the resulting differential output, VOD. And this will never have a DC component. If you take just here and here, you will have some of this VCM also impacting that, right? But if you take it differentially, if you take the output differentially, then what is being told us here is that you will get only a pure signal component on the output and nothing related to the biasing appears on the output if you take the output differentially, okay, which is VOD in this figure. So make sure you see the point, the difference. Okay, we'll continue on and actually do some small signal analysis. So for small signal analysis, first of all, I want to make the point that GM denotes the equal transconductances of the two devices. So Q1 and Q2 are assumed to be perfectly matched. They have the same GM. Not one of them is 100, another 200. No, they both have the same, which is a bit of a unrealistic situation, but for the analysis, that's what we assume. Also, what you'll notice is compared to this previous circuit where VDD is mentioned, VSS is mentioned, the biasing current source I is shown here. All that is gone, right? So biasing stuff is taken away, removed, and we assume that the circuit only has the input signals and the output signal and nothing else, right? Which is generally how we have done small signal analysis. Again, to repeat an important point, this way of doing a small signal analysis is only allowed if you are in the linear operating range. The linear range of the saturation curve of these two devices is where you're allowed to make those assumptions. So, figure 8.8b, the circuit is shown with the power supplies grounded, the bias current source I removed, and VCM eliminated. That is, only signal quantities are indicated. Now, one more way to understand this is that to perform small signal analysis, you can take the bias voltage sources, replace them with a short circuit, and take the current source and replace it with an open circuit. Remember when we were studying Thevenin's theorem many years ago and we were creating a way to measure Thevenin's resistance from the output terminals? The rule we were told was you should short circuit DC sources or DC voltage sources and open circuit current sources. So same logic here. If you have a VDD, just replace it with a short circuit. And we had a current source here, open it. So what you're left is a circuit on which you can do simple Ohm's law and KCL, KVL to understand the resulting voltages and currents. Okay. So let's look at this in some detail. So even though we don't show the current source, we know that Q1 and Q2 are carrying equal values of I by 2. That means I, the current source, the biasing current source, is divided into two portions. One of them is here, one of them is here. So the input signal at the gate is VID by 2. Here, the input signal at this gate is minus VID by 2. So if this is a sinusoidal input, you can kind of assume that the positive half of the sinusoid is going here and the negative half goes here, something like that. So VID by 2 and minus VID by 2 are applied respectively to the gates of Q1 and Q2. The output voltage at this gate, at this drain VO1 is given as the input multiplied by this gain factor, transconductance GM times the resistance, right? We have seen this formulas previously. The current flowing in here is V by R, right? Voltage by resistance. The voltage applied is the signal or half of the signal. GM is a conductance, which is 1 by resistance, right? You know that. So the current here is GM into VID by 2, which is the same current here because this is a return path. So a virtual ground or a point at 0 volts appears at the common point, which is the connecting point of the two sources. And then you can imagine the current coming in and going out. So the current, obviously this is the output, right? So the current isn't going here. It's going just into whatever is, let's say there is a load resistance, and the current is going into that load resistance in this form, okay? Because of the presence of the signal voltage. So make sure you follow that logic there. The signal voltage is the source. A plus is applied here and a minus is applied here. And that is driving a current through the two transistors and through the load resistance that is applied somewhere here between the two. Okay. So output voltage, if you want to take it single-endedly, that means if you just want to take a voltage from here to ground, that value is this. If you want to take a voltage from here to ground, that value is this, VO2. This is plus, this is minus, and they're equal. If you just want to take the differential output, then it's this minus this, which comes out to be this. GMRD VID. Okay. So I spent a few extra minutes on this just to make sure you follow the logic. As soon as we replace this with the, actually in the textbook you can see where the T model has been introduced, because we know that MOS transistors can be replaced with a small signal model that you can then use for the analysis. So we are kind of seeing just the results of that analysis. And whatever we need to know about the input voltage and the relationship between the input and the output voltage is shown in this drawing. Here, I guess one last thing they want to talk about is figure 8.8c shows the total resistance in the source circuit of 2 by GM. So 1 by GM is the resistance here. Another 1 by GM is here. If you add the two, then it's 2 by GM. And the signal current ID, which is these currents, can now be shown to be VID by 2 by GM. Okay. So that's one more way of visualizing what happens in the small signal domain. Okay. So that is about the simplified version of the small signal. Definitely take a look at the textbook where he also brings in the T model to help us go from pure um, input signal circuit to coming up with these formulas which are the result of the small signal analysis. So spending a little time reading the section entirely in the textbook will also be beneficial. But based on what we just saw in the previous slide, you can see that these formulas now start to make sense. So GM we know is always 2ID by VOV, 2 into I by 2 by VOV. He's shown this separately. So you can say that's I by VOV. Now the current ID is half of I, right, in each transistor. So if you want to write GM in terms of the current source value I, then it's I by VOV. Normally if it is just a single transistor, we use this formula, 2ID by VOV. Similarly, the output voltage, single-ended output voltage, VO1, in terms of the input voltage is GMRD by 2 VID. Similarly, output 2 is GMRD by 2 VID. So you can see whatever was shown here is kind of written in this way. Now, gain, which is the output by input, has two definitions. One gain is single-ended output, another gain is differential output. Single-ended output is VO1 by VID or also VO2 by VID, and notice that one of them is a negative and one of them is a positive. The magnitude is the same. Assuming GM and RD are perfectly identical, the single-ended output or the gain is half GMRD. The only thing is one of the output voltages compared to the input will have a negative sign and the other will have a positive sign. That means if you are taking an output from VO1 and it's a sine wave, you can assume that the sine wave will appear on the output in an inverted fashion. That means it will be out of phase by 90 degrees. The other definition of gain is differential output, right? Differential is when you're taking the output between O1 and O2 or terminal 1 and terminal 2 or drain 1 and drain 2. Then the output VOD is defined as VO2 minus VO1, like VO2 minus VO1 divided by the input, that's the gain, and you get GMRD. So if you compare this GMRD to either of these single-ended outputs, what you see is you get a double the value because the term half goes away. So you get double the gain, and that double the gain actually is 6 dB higher. Remember, this is voltage gain. If it was power gain, it would be 3 dB higher because a double means 3 dB with power. But with voltage, you use 20 log V2 by V1, right? So differential gain in this case is 6 dB higher than single-ended gain. Now the last thing I want to point out is in all this analysis, we have ignored the output resistance of the devices, the intrinsic output resistance RO, the small RO, right? If that's the case, then the formulas are simpler. But if that RO cannot be neglected for whatever reason, then you have to put this formula RD in parallel with RO to get the gain. Okay. So these formulas are important. The differential gain output, or the differential output gain, the single-ended output gain. Again, this entire analysis we have ignored common mode signals. We are only focusing on differential signals. We are assuming that there is no need to include common mode because the devices are perfectly matched. The power supplies are also, complementary completely. So we are focused only on differential gain. We have some problems on this section, which we may come back to either in this recording or the next one. But for now, I'll skip this slide 27, 28, 29, and we'll stop at a topic called differential half circuit. So sometimes it helps to think of the differentials pair as consisting of two halves. If everything about the two halves is identical, that means if we can say it's a symmetrical differential amplifier, that means Q1, RD, they are exactly the same for both. Also, it is fed with a differential signal in a balanced manner. That means we have VID by 2 here, and the other half VID by 2 goes to the other gate of Q2. If that is the situation, then the analysis can be done by only looking at one half. This is a simplification and it sometimes helps. But the point is, you can talk about something called a differential half circuit, where you just cut off the other half, just focus on one half, and you can still come out with a value for the output, VOD by 2, and the differential gain is AD equals GM RD parallel RO. Apparently, this is more useful when RO has to be considered. And we'll do some examples to understand this half circuit business a little better. Yeah. So here in example 8.2 in the textbook, he takes one full differential circuit and cuts it up into two halves and shows us how to work only on one half. But we'll wait to do this in the next recording. All right. Moving on to the next topic, we are still on the differential amplifier, but now we start to add some of the more advanced things that we have learned, such as current sources, current source load, and then cascading. I'm sure you remember, or maybe you've forgotten entirely, but a couple of weeks ago we studied what current source loads are. In a simple MOSFET circuit, if you take out the drain resistance RD and put a PMOS device which provides a fixed current, then such an arrangement was called a current source load. So, in addition, we were told that if you use such a current source load, first of all, the nice thing is in integrated circuits, we don't like resistances, so you can get rid of a resistance by just having one more active device, the PMOS. So that's one big benefit. Second benefit is that your gain can be improved by using current sources, but we also studied that you need cascading. Otherwise, the benefit the the voltage gain that we hope to get will not happen without cascading. So it's a two-step process. First, you got to get rid of the resistance in the drain circuit, put a PMOS device. Then secondly, to achieve the real gain, you have to take each of these transistors, the gain transistor, put another device called a cascade device. Similarly, you take this current source transistor, the PMOS transistor, and put another PMOS to call it a cascade. So two extra devices, and then you get all the great benefits, which is higher voltage gain, higher output resistance, and all that. So the same ideas that we studied for just working with one gain cell transistor, now we can apply even in the differential configuration. All that happens is previously we had two transistors to worry about with simple current source load. Now we have four to worry about. Similarly, if you go on to cascading, and I skipped ahead a couple of slides, previously we only did the analysis on this one part. Now we have another part here to worry about. But we've learned some techniques like half circuits and all that to simplify the analysis. But the point to be made is, and I'm going back to slide 32, is that the technique of current source load and cascading can be applied to differential amplifiers also. What happens to the formulas? So let me quickly read this. To obtain higher gain, the passive resistances RD can be replaced with current sources, with cascading, of course. The current sources are realized with PMOS transistors Q3 and Q4. And VG is a DC bias voltage that is required to ensure that Q3 and Q4 each conducts a current also equal to I by 2. So whatever current is here, I, which splits into two halves, also flows into Q3 and Q4. But to make sure that happens, your VG has to be appropriately chosen. Okay? And you can do the analysis of this using the half circuit approach also. And see how the inputs are still applied differentially. There's a VCM plus VID by 2 and a VCM minus VID by 2. The output can be taken differentially also. The differential voltage gain in this configuration is GM1 into RO1 in parallel with RO3. So it's not just RO1 anymore. It's RO1 in parallel with RO3. There's no RD, right? That is gone because there's no drain resistance. But now we start to consider the intrinsic resistances RO1 and RO3 in the formula. You can also say the same thing on this side. You can say the formula for AD is GM2 into RO2 in parallel with RO4. If the devices all have the same transconductances, then the formulas are identical. As you can imagine, we have some problems. We'll come back to do this. Here is the cascaded version of the same differential amplifier with current source load. So I won't go too deeply into this. I think by now you know how this works. The output is taken here. There's the gain cell and a cascaded transistor for the gain cell. There is a current source load of the opposite type, PMOS, and it has its own cascade, PMOS. The total gain, voltage gain, if the output is taken differentially, is VOD by VID is this. Now you have RON and ROP. RON is the N devices, the two at the bottom, their net output resistance, which is given by this formula, and then ROP, which is given by this formula. So it's a little more complex, but as we do some problems, you'll understand, I think, better. But we know that by this arrangement and spending so much money on all these transistors, extra transistors, your gain goes up by almost a square factor, right? If you have a basic gain of, let's say, 10, with all this arrangement, you can get almost 10 square or close to 100. Where 100 is too much for these, but maybe it goes from 3 to 9 or something. Okay. All right. If all transistors have the same channel length, are operated at the same VOV, assuming that they have the same early voltages, then apparently the differential gain voltages has the square factor. AD is 2 VA by VOV square. And we'll do some problems on this, at least one problem. All right, I should move on. We have an important topic to understand in the next 10 minutes called common mode rejection ratio, CMRR. So common mode gain, I think we've already studied that a little bit. If the ideal current source with infinite output resistance, the current common mode gain is 0. If it's a real current source having a finite resistance RSS, we are talking about this current source at the bottom here. So we are neglecting, for defining this section, for the moment, we are not looking at cascode and current source load. We are back to the regular differential circuit with drain resistances, RD. So let's define what is common mode gain. If you have an I with a real finite output resistance RSS, that RSS comes in parallel with the I, and the common mode gain will no longer be 0. So here, note that there is VCM and there's VICM. But this VICM is not a signal. For the moment, we are assuming it's some kind of noise. It's not data, it's noise. So what we'll do here is to analyze the common mode gain in the presence of some such disturbance. Not real data signal, but some kind of noise signal. Okay. So we have a symmetrical circuit with Q1 and Q2, and RD is exactly the same. The common mode gain, which we've already seen before, is not anything new, but this time we have an RSS to worry about. If you remember the previous analysis, this was an open, right? And this was a common ground point. But now between this point and here, we actually have another resistance. If such is the case, and you have an input signal VICM, which is an unwanted input signal, then that appears on the output also. And so the common mode gain can be defined as, if you're taking it single-handedly here or here, VO1 by VICM, which is VO2 by VICM, is minus RD by 2 RSS. Okay. So this is derived based on this. where RSS is subject to certain conditions, then the common mode gain, either here or here, is defined by is equal to this formula RD by 2RSS. Now if you're taking it differentially, this is 0. Okay? We are only concerned when we are taking it single-endedly from here or here. Okay? This is when Q1 and Q2 and RD are exactly the same. Now, in a real circuit, in a real situation, there may be two ways that the circuit is not symmetrical. Either the RDs are not matched and they are slightly different, RD and RD plus delta RD. In that case, the common mode gain, which previously we said was 0, right, will not be 0 anymore, but it will be a certain definite value given by this ratio minus delta RD by 2RSS. So see what we are doing here. We are trying to understand in a real circuit with mismatches of the two resistances, the output voltage cannot reject the input common mode voltage. We all along we have said that a differential circuit, the greatness about it is that common mode disturbances will be rejected. They will not appear on the output. Now we are starting to realize that in real circuits, some of the common mode signal can appear on the output. And there is a definite gain, ACM, common mode. This is because of the mismatch of the RD. Similarly, we have another condition where the Qs are mismatched. That means the GM, the two transistors are mismatched because maybe there's a W by L mismatch or a GM mismatch. Then also there is a common mode gain which is not 0, which can be given by this formula RD by R2RSS times delta GM, which is the difference in GMs between the two devices, by GM. So there are two ways then, and I'm going to neglect this for now. There are two ways that common mode gain also appears and is not 0. Now we define CMRR. CMRR, which we have seen before, I think, when we studied op amps, but now, back then we neglected it, but now we cannot. So CMRR is a measure of the effectiveness of the differential amplifier in amplifying differential mode signals and rejecting common mode interference. So a differential amplifier has to do both things. Differential signals, it has to amplify. Common mode signals, it has to reject. And if you take the ratio of the magnitude of the differential gain to the magnitude of the common mode gain, so if you take CMRR as the ratio of the differential gain to common mode gain, which can also be shown in terms of decibels, that is the definition of CMRR. That tells you how good the amplifier is in doing its job, which is to amplify differential signals but reject common mode signals. And we know that common mode gain even comes into the story because of the effect of RD mismatch and the effect of GM mismatch. So CMRR can be written in terms of the RD mismatch by this formula, or or GM mismatch in this formula. And if both of them exist at the same time, RD and GM mismatches, then you can find ACM. AD is the same always, GM RD. Then you can take the ratio. So CMRR, a high CMRR means the amplifier, the differential amplifier is doing a good job. Low CMRR is a bad job. And we'll do some problems in the next recording to understand CMRR a little better. Let me stop for now.